In this lecture, we will see some problems. First, some problems based on half-life period. The decomposition of a substance follows first-order kinetics. The half-life period of the reaction is 35 minutes. What is the rate constant of the reaction? So in this problem, we have to find the rate constant. And what is given is half-life. So T half is given as 35 minutes. For first order reaction, we have expression T half is equal to 0.693 by K 1. So we have to find K1. K1 is equal to 0.693 by T half, which is equal to 0.693 by 35 minutes, which is equal to 0.0198 minute raised to minus 1. The rate constant of a first order reaction is 10 raised to minus 3 second raised to minus 1. How much time will it take for 10 gram of the reactant to reduce to half? So in this problem, we have to find T half and the rate constant K is given. So for first order reaction, T half is equal to 0.693 by K1 and K1 is equal to 10 raised to minus 3 second raised to minus 1. Therefore T half is equal to 0.693 divided by 10 raised to minus 3 second raised to minus 1. This is 0.693 into 10 raised to 3 second, which is equal to 693 seconds. The half-life period for thermal decomposition of acetone at 873 Kelvin at different initial pressures are given in the table. So initial pressure is varied from 98 to 230 to 296 and the T half values are given as 86, 85 and 86. So from the data it is clear that T half is independent of initial concentration, since T half is same whatever be the initial concentration taken. This is characteristic of a first order reaction. So this is a first order reaction. Now two homeworks based on this. Calculate the half-life of a first order reaction whose rate constant is 200 second raised to minus 1. A substance decomposes following first order kinetics. If the half-life of the reaction is 35 minutes, what is the rate constant of the reaction? Another simple problem. The decomposition of H2O2 has been found to be first order with a rate constant 7.3 into 10 raised to minus 4 second raised to minus 1. Calculate the rate of the reaction when concentration of H2O2 is 0.25 moles per liter. Second one, what concentration of H2O2 would give a rate 7.49 into 10 raised to minus 4 moles per liter per second? So we know it is given that it is first order. So expression for the rate is equal to K into concentration of H2O2. Here they have given the rate constant as 7.3 into 10 raised to minus 4 second raised to minus 1. So K value is given and you are asked to calculate the rate of the reaction when concentration is 0.25 moles per liter, the first one. So concentration of H2O2 is given as 0.25 moles per liter and K is given as 7.3 into 10 raised to minus 4 second raised to minus 1. substitute, you will get the answer. Rate is equal to K is 7.3 into 10 raised to minus 4 second raised to minus 1 into 0.25 moles per liter. The answer for this is 1.825 into 10 raised to minus 4 moles per liter per second. Now B part is, if the rate is 7.49 into 10 raised to minus 4 moles per liter per second, then what would be its concentration? So same expression is used here. Rate is equal to K into H2O2. Here we have to, they have given rate, K is known. We have to find out what is H2, concentration of H2O2. So concentration of H2O2 is equal to rate divided by K. Rate is given as 7.49 into 10 raised to minus 4 moles per liter per second, and K is already given in the beginning, which is 7.3 into 10 raised to minus 4 second raised to minus 1. Substituting, we will get H2O2 concentration is equal to 7.49 into 10 raised to minus 4 moles per liter per second divided by 7.3 into 10 raised to minus 4 second raised to minus 1. So second raised to minus 1, second raised to minus 1 got cancelled, and you will get the answer as 1.026 into 10 raised to minus 4 moles per liter. You have a homework similar to this. Note it down. This problem is just like one discussed earlier. Instead of decomposition of H2O2, here you have decomposition of N2O5. They have given the first order rate constant. You have to calculate the rate of the reaction when concentration of N2O5 is 1.25 moles per liter, and also when it is 0.25 moles per liter. Then you have to calculate what is concentration of N2O5 if the rate of the reaction is 2.4 into 10 raised to minus 3 moles per liter per second. The decomposition of benzene diazonium chloride follows first order kinetics at 232 Kelvin. The value of specific reaction rate is 7.09 into 10 raised to minus 2 minute raised to minus 1. Calculate the rate of reaction if the concentration of reactant is 1.9 into 10 raised to minus 2 moles per liter. Here the specific reaction rate is nothing but the rate constant. So for a first order reaction, we know rate is equal to K into concentration of the reactant A. Here the reactant is benzene diazonium chloride. K is given as 7.09 into 10 raised to minus 2 minute raised to minus 1, and concentration of benzene diazonium chloride is 1.9 into 10 raised to minus 2 moles per liter. So just substitute. Rate is equal to K into concentration of benzene diazonium chloride which is equal to 7.09 into 10 raised to minus 2 minute raised to minus 1 into 1.9 into 10 raised to minus 2 moles per liter. On multiplication we will get 1.347 into 10 raised to minus 3 moles per liter per minute. We'll summarize the characteristics of first, second, third and zero order reactions. First we'll see first order reaction. For a first order reaction, the rate is proportional to concentration of reactant raised to 1. So R is equal to K into A. Second is regarding the integrated rate law. This is given by K1 is equal to 2.303 by T log A divided by A minus X. Third one is regarding a graphical representation of this. For that, we have to rearrange this equation. K1 is equal to 2.303 by T log A divided by A minus X. When you rearrange this, we will get K1T divided by 2.303 is equal to log A divided by A minus X. Or K1T divided by 2.303 is equal to log A minus log A minus X, or log A minus X is equal to minus K1 divided by 2.303 T plus log A. This equation is of the form y is equal to mx plus c. When you plot log A minus x in the y-axis and time in the x-axis, you will get minus k by 2.303 m. This is the slope, and log A is, you will get the y-intercept. Along the y-axis, you have log A minus x, and x-axis you have plotted time t. So you will get a line with a negative slope. Slope is equal to minus k1 by 2.303, and this is the y-intercept log A. Fourth characteristic is regarding T half. T half is independent of initial concentration. And fifth one is the unit of rate constant. Unit of rate constant is time raised to minus 1. Next we will see the characteristics of second order reaction. So characteristics of second order reaction are: first one, rate depends on concentration of the reactant, the whole square, that is R is equal to K to A square. The integrated rate law is given by K2 is equal to 1 by T x divided by A into A minus X. Third one, a graphical representation. For that we can rearrange the equation. K2 is equal to 1 by T x divided by A into A minus X. K2 is equal to 1 by T 1 by A minus X minus 1 by A. K2T is equal to 1 by A minus X minus 1 by A, or 1 by A minus X is equal to K2T plus 1 by A. So this is of the form y is equal to mx plus c. So if you plot on the y-axis 1 by A minus X and x-axis time, you will get a slope of K2 and y-intercept 1 by A. Here 1 by A minus X, here T, slope is K2 and y-intercept is 1 by A. Fourth characteristic is T half is inversely proportional to initial concentration. And fifth one is unit of rate constant is liter mole raised to minus 1 time raised to minus 1. Now we will see third order reaction. The characteristics of third order reaction: rate of the reaction depends on three concentration terms. O rate is proportional to concentration of reactant in the whole cube. R is equal to K3 into A cube. Second one is the integrated rate law, which is 1 by 2t x into 2a minus x divided by a square into a minus x the whole square. Third one is T half is inversely proportional to the square of initial concentration. T half is proportional to 1 by a square. And fourth one is unit of rate constant is liter square mole raised to minus 1 time raised to minus 1. Finally, the zero order reaction. The rate of reaction is independent of the initial concentration. That is, rate is proportional to concentration term raised to 0. Second one is the integrated rate law, which is x is equal to K0 into 3. Third one, graphically, from the equation x is equal to K0 into t, this is y is equal to mx plus c. If we plot on the y-axis x, on the x-axis time, you will get a straight line passing through the origin because the y-intercept is 0. Y-axis you have x and x-axis you have time. You will get a straight line whose slope is equal to K0 and y-intercept is 0. Fourth one, the unit of rate constant is moles per liter per time. And finally, T half is proportional to the initial concentration.